So yeah, I'm going to talk a bit about some work I've done in Cambridge in the lab of Paul Bays, starting with kind of older work that I've already presented in the summer school, just briefly going over that about the idea of binding via space, and then some results on how to adapt that to binding via time. So yeah, as I think everyone here knows, visual working memory is a limited capacity system for short-term storage and manipulation of visual information. And in the system, we frequently, it's critical that we encode not only what is there or what features are there, but how these features are combined. What features are at what locations, what shapes are associated with what colors. For example, if you're playing chess and planning your next move, it's of course very important that you know not only what pieces are there and that there are black and white ones, but what particular piece of what color is on which field in order to play the game. And the binding problem, or one aspect of the binding problem, is how the neural system achieves necessary flexibility in presenting this visual information. One challenge there is that visual features as we think of them are generally encoded in the population codes. So we have a lot of neurons that have different tuning curves, for example, for color and for location. In order to cover just the simple combinations of like here this mock-up of a psychophysical task, where a color dot can appear at different locations with at a fixed distance from the center. To present information in that in a population code, you already need a lot of neurons that basically cover all possible combinations of this just one-dimensional location, in the circle around the center, and the color. So each individual neuron has a tuning curve for location and color, and responds maximally only when both of the features match its preferred values. The problem becomes even more challenging if we consider many features, and if we consider two-dimensional space. That's actually not even included yet in this figure. But yeah, if we wanted to combine all possible or represent all possible feature combinations in a single population code, we would need a huge number of neurons to cover all possible combinations. And so one proposal that we made quite a long time ago is that instead of having a complete combination of all features, we only have individual feature maps over space. So here shown for color and orientation over just one-dimensional space. And of course, in the robotics world, people in Bochum and in Portugal as well use three-dimensional neural fields over two-dimensional space and typically one-dimensional additional visual feature. And so yeah, this proposal, or the proposal that we come up with these feature maps over space, is that not all features are bound to each other directly then, like color and orientation are not bound in a conjunctive population code, but only indirectly via space. So by having the same locations occupied by different features in these different fields, we can at least indirectly retrieve, for instance, an orientation that is linked to a certain color by choosing its location first and then retrieving the other feature. And that was in part also motivated by this idea that the spatial information also has to be transformed, which in itself is a difficult process that requires high-dimensional fields. And so separating that out and transforming it separately made a lot of sense to us. Now, in Cambridge, I've done some psychophysical studies where I tested this idea of binding via space. And I think pretty much everyone here already knows that, or has heard of it before, perhaps. So I go over it relatively quickly. The type of task that we used here is a dual report task in which participants, by the way, can you see my pointer? Yes?
Yes.
Okay. So participants viewed a visual display with multiple stimuli, which each of them was a colored and oriented bar, and they had to memorize, well, everything in there, so all the colors and orientations of these individual bars. And after a brief delay, then after the display was taken away, they were either cued within the orientation of one of the bars, and they had to report then with this kind of response style by adjusting on a continuous scale both the color and the location of the item. So first adjusting to set the right color. For example, in this case, this orientation matches this bar here. So they have to set the blue color, and then they have to adjust the dot appearing to the location of that item. There's a second condition where they are cued with the color, and they have to report in the same way then the location, the orientation of the item with this color, and the location of the item.
The location is one-dimensional along this circle.
Yes, exactly. All the items appear at the same distance from the center, so it's just basically on the circle around the center.
Yeah.
There would be a potential third condition where you're queuing with location. We didn't include that here because that was already done before. And the finding there was not with a lot of model fitting, but the general finding was that errors occur independently for orientation and color. Which indicates already that not all features are very tightly bound to each other. You can make errors independently for different features. Now we considered here two possible mechanisms of binding for this task. We didn't consider this very high-dimensional kind of model where everything is bound together, but only conjunctive feature codes, conjunctive population codes between two features. And the first one would predict or would be just direct binding of the Q feature. So in this example, the color, and the two other features, so the location and the orientation. Whereas the other implements this idea of binding via space, where color and orientation are only bound to each other indirectly. To retrieve the orientation that's associated with a certain color, you have to first retrieve the location where the color was in the display, and then use that as a secondary cue to retrieve the orientation of an item. Whereas here you can do directly, you put in the color. If you have a direct population code reflecting color orientation conjunctions, you could retrieve the orientation response directly from the color cue. Yes, there's a question.
And is the assumption in the left case such that you would assume that there is a third field that binds the location with the orientation as well?
Yes, exactly. You would assume that there are all possible combinations are reflected. Just in the case that you get a color cue, then you only need these two fields to respond.
Yeah. All right. Thank
you. Okay. Right. And we can distinguish these models based on what predictions they make regarding supposed swap errors. So swap errors are a type of error that you can observe in all of these kind of continuous report tasks. That most of the time people will make the right response, depending on how difficult the task is, but that should be the majority of responses. Meaning the right response to color or orientation value that is at least in the close vicinity of the correct value. Sometimes people will make large errors, and a lot of these, or at least a certain part of these large errors, are basically responses with features that were there in the display, but don't belong to the Q target item. For example, if the participant saw this display and is cued with this kind of orangish color, they might actually report the location of the item up here, which has a kind of similar color, but it's not the correct target item. That would be this one, I guess. And the question is then, if such a scenario occurs, what kind of orientation response should the participant make? And in the case that we have these separate representations for all feature conjunctions, the orientation response shouldn't be affected by this error occurring in the location response. They still have the Q color and can associate it directly with the orientation, and so most of the time they should still report the correct orientation, although it might of course happen that they make another swap error there as well. That prediction is plotted here. So here the typical or one way to present performance in these tasks is to plot the distribution of responses relative to the target value. So that the response error on the x-axis, 0 at the center would be a perfect response. Minus pi to pi is the range of kind of errors that you can make in this task. All the features are on the circular space. That's why it's minus pi to pi. And you see here actually a model already fitted to the data we got in this task for the orientation report over all trials. And yeah, participants, at least a lot of the responses are distributed around 0. But you also see there are quite a lot of, quite frequently there are larger response errors. And this prediction that the model made about the orientation report, so this would be the orientation report of all trials. Now looking only at those trials where the spatial response was wrong. And so where we think the spatial response was a swap error, which you can tell relatively clearly because the spatial response is precise. So if the spatial response is very close to one of the other items, the other item locations, then we can say with relatively high certainty that it was a swap error. The participant kind of selected one item, but it's the wrong item. And this direct binding model would predict that, as I just said, the responses in this orientation report for the spatial swap trials should look pretty similar to the orientation response over all trials. So the response error should be centered on 0, and yeah, most of the responses should be more or less correct. And the second plot shows the deviation from the item at the reported location. So how far should the response on average be, or over all trials be, from the item, from the orientation of the item at the location they have selected. And here the distribution should be broader with a smaller peak, with a smaller peak just reflecting the cases where they by chance make the same swap error both for the location and for the orientation response. In contrast, in the binding wire space, you can imagine that if you here make a swap error in the location response, so you have selected the wrong location, then we would expect that that location is also what you use to retrieve the orientation, which you can only get to from the location information. And so you would have a consequent swap error in the orientation response as well. And so here the prediction was that you should almost never respond with a orientation that is the correct one, with a target orientation, but your orientation, your response should be really centered strongly on that orientation of the item at the selected location. And the peak is even steeper here because you, in these orientation responses over all trials, you still have all the location errors in there. In this one, you have already kind of picked the location that you have selected, that you have used as a cue. And so you should be more concentrated in your orientation response on this wrong item. And that is exactly what we found in this task. So the dots here are the actual behavioral results, and they closely match the predictions of the spatial binding model and not of the direct binding model. And yeah, so we concluded that binding via space is actually the strategy that is used in this task. These correlated errors in the spatial and the color or orientation response support that you make the same swap error. So if you make a swap error in your spatial response, you make a corresponding swap error in your other feature response. And we got consistent results here, both when tuned with color and when tuned with orientation and reporting the other feature. And I should also note that we actually, although I showed it here as basically first making the location response, in the actual experiment, the order was opposite to that. So you always had to report the color or orientation first, and only afterwards the location. so that the response that you made shouldn't influence your feature response. But the results indicate that nonetheless you always select the location first and then use that to select the color, and then afterwards report that selected location in your second response. Yeah, that was confirmed by formal model comparison, tailoring the spatial binding model very consistently over both conditions. And yeah, the previous results of that I mentioned at the very beginning, that if you do Q with location in this kind of task, you see uncorrelated errors for color and location, for orientation and color. Q with location, get independent errors for the other features. That indicates that there's not really a kind of fully bound representation of all the features, which would in these tasks that I've shown make the same predictions as the spatial binding model, but that really there's a difference in whether you queue with location or you queue with another feature, and location seems to have a special role in that only it is bound directly to the other features. Okay, so that was the spatial binding part. Now, limitation of that is, of course, that items can be separated in time rather than space, so they can occupy the same location at different times. That's very clear in the example of the chess game that I started with. That, of course, if I'm planning a move, I may think that, okay, now I'm striking out that piece, and now another piece is going to be there, and they're going to occupy the same location just at different times. And you still have to keep them apart and remember both of them. And yeah, a pure binding by a space account could not explain that. If that really was the only way you could connect other features to each other, then you should completely lose the binding information or be kind of respond randomly, or kind of at least make random binding errors when multiple stimuli occupy the same location.
And so by that, you mean that, for instance, if there are multiple objects or components of object at that location, then you wouldn't have a possibility to store all those. And then you're hypothesizing that you could maybe sequentially attend to the different components. Is that sort of the idea?
Yes. So the idea or the problem is that, say you have the example of a green square and a red circle, and they are presented one after the other at the same location.
If it's sequentially presented, yeah.
Yeah.
But let's say, and that's what you do in your experiments, but if you think logically, is the thought that if you had a more complex object, you might be attending to different components of the object.
That's also right.
At different moments in time.
Yeah.
Yeah. I see. Okay.
Yes, I mean.
But that's not what you probed, right? You probed.
No, we didn't probe that. We really probed kind of items that are separated in time. But I guess the problem, of course, occurs for both cases, that if you really have just these feature maps over space, and you will, even if, I mean, you can have multiple features at the same location, depending on your exact connectivity. But if you have two colors and two orientations at the same location, you could no longer distinguish which of these colors belongs to which orientation if they're only bound to each other via this location information.
I mean, there is this work from Hazeltine's lab. I never remember if it was Hazeltine or Hazeltine. No, that Jonas Lind's tried to model, where illusory conjunctions were more frequent when items were close to each other. That would be sort of related, right? That would be consistent with that thought that there's a difficulty here.
Yeah, and that's actually exactly what we first looked at, what was the experiment that inspired and or motivated the ultimate binding by time approach. So there have been some previous study that also probed items being presented at the same location and compared the performance there to items at different locations, and they found an impairment in binding. So here this task is illustrated that was used there. So you also have to remember 4 color-oriented bars and report, for example, the retrieved color and then report the associated orientation. And the bars were always presented sequentially. but either all at different locations, so one by here, one there, and one there, and one here, or all sequentially at the same location. So presented relatively quickly, just 200 millisecond presentation time, 300 milliseconds interstimulus interval, so break between the stimuli. So one item at the other here would be presented at the same location. And what that study found was that, yeah, there was an impairment in binding, there was indication for that, in the form of an increased number of swap errors. So people more often reported an orientation that didn't belong to the color that they saw. That was there on the display, but wasn't the right one. And that at least suggests that, I mean, people weren't a chance nonetheless, but at least it suggests that there was that was more difficult, so that maybe they had to use some kind of secondary mechanism to solve this task because they couldn't use space as a binding dimension here. However, my colleague Will Harrison in Cambridge, he did an experiment that actually looked specifically at interference from nearby items. So this what's called that's basically flanking items impair your perceptual performance for central stimulus. So if you have two orientations around the stimulus, around one oriented bar, then your perceptual performance for that is impaired. And they also tried something there with sequential presentations, and they had some conditions that were kind of similar to this task here, in that items didn't appear at exactly the same location, but at very nearby locations, and there they didn't find any impairment in the performance. So there was no increase in swap errors. And one difference was that the items they were presented a bit more slowly, a bit more time in between. And so we repeated the task. Crowding is the word I was looking for. So temporal crowding or spatial crowding. We first reproduced, or in this task, we reproduced first the findings from the original study from Professor Hussein. And then we simply increased the presentation time to 500 milliseconds and the interstimulus interval to 500 milliseconds. So this is the proportion of swap errors observed when items are presented at different locations or at the same locations. In relation to the original study, there were more swap errors when items were presented at the same location. But when we increased the presentation time and the interstimulus interval, then that effect disappeared, and participants were basically just as good in both conditions. So that indicates that then that having only one location where everything appears isn't such a big problem for visual working memory. The challenge was how can we, or what other mechanism is there other than spatial binding? And kind of a natural alternative is to use then time as the binding dimension in the same way. So in that case, you would have features like colors and shapes now bound to kind of a point in time rather than to a point in space. So to the time when they were presented, or perhaps when they were attended, and still have no direct binding between these features. And we compare that again to an account that assumes really bound objects, and that is still a popular idea in the kind of computer science community, that you have these object files or some kind of bound object representations where all the features should be stored together. So we use a task that kind of tries to emulate this idea of this spatial binding task, now with objects separated in time. So we presented just 3 sample stimuli, colored shapes, always basically at the center, for 400 milliseconds and 500 milliseconds interstimulus interval. So what we found in the previous study was enough to basically resolve this temporal crowding problem, followed by a brief mask. And then again, we asked, or we queued with one feature, and participants had to report the two other features. So we could queue with an ordinal position, so 1, 2, or 3. And participants then had to select the color of the item presented there and its shape. Or we queued with a shape, and participants had to report again the color and then the ordinal position, so first, second, or third item. So this ordinal queue condition would be basically corresponding to a spatial queue condition that we didn't explicitly do in the previous task, but as I said, has been done before. So that should be bound directly to the features in this binding by time approach. And this would be have to be resolved indirectly in this account. We have some details on the stimuli that we used. So they were taken from continuous feature spaces, kind of a color ring, and this kind of parametrically modulated shapes. The reason I didn't want to use orientation here is because in orientation you can have kind of a natural ordering of the orientations. If they're somewhat similar, like you can have this, and this, and then it's kind of like a motion from one orientation to the next, and they're kind of in a natural order. In some of the trials, while they go back and forth in the other, so there may be some sort of motion or direction perception there that could be used to retrieve items that we didn't want to deal with, and they could make some trials easier and others harder. So we chose these shapes, intended to be sufficiently different but hard to verbalize, so that people could respond or memorize them, but had to really rely on their visual memory. We made discrete response options rather than having a continuous response to make the different features more kind of symmetrical, because the ordinal position would be discrete in this task. We didn't really want to make it too complicated with kind of different time intervals. Also we did find that the task, so you saw maybe in the previous task with spatial binding, we had 6 stimuli. Here we have only 3, because we did find that presented items sequentially did make the task quite a bit harder. And having a kind of faster response and discrete response options alleviated this difficulty a little bit. Okay, let's move to the two conditions again. Participants always had to click first on the color, then on either the shape or the ordinal position. Here are the results, the overall results from the conditions. It's a slightly difficult plot, complicated plot that tries to capture all the results. So we have proportions of responses, target responses, so selecting the color or the shape that actually was at the queued position or that was associated with the queued shape. Swap responses, meaning selecting one of the features that was there but didn't belong to the queued target item. I should have mentioned that here. So the options were always the target, of course, the 2 other features that were present, and a foil feature, so a color or shape that wasn't actually present in the display. For the ordinal position, of course, there wasn't a foil because participants knew that there were 3 items, and did make sense. Okay, and here in blue are the reports of the results from the color report in the ordinal queue condition, and orange the shape report. And there's always 3 individual bars because performance also varied with which item was the target item. As you can imagine, so there's a recency effect that if the 3rd item was queued, then performance was better than if the 1st item had to be reported, simply because the 3rd item, of course, is more recent. Overall, performance then was reasonably good. it was a bit better with the color report and the shape report. In general, we did find that people made, so that if subjects made errors, it wasn't completely random. So there were more swap errors than you would expect by chance compared to foils. We also found that the ordinal queue was easier in that people were better in the color report with the ordinal queue than with the shape queue, which would be consistent with the binding via ordinal position or via time, but is not very conclusive yet. So to analyze, to kind of distinguish between these two models, we first kind of formalized them by determining response probabilities or conditional response probabilities. So these in the form of these confusion matrices for different feature combinations. So for example, we took all trials and looked only at one Q response pair. So for example, here would be the color report given the ordinal position. And we can then create a confusion matrix. If the first item was queued, what is the probability that you report the feature of the first, the second, the third item, or the foil color? And the same if the second item was queued, and so on. And that kind of reflects these performance differences from depending on the ordinal position of the queued item. And also the kind of probabilities of confusing two items, which was a bit higher for the two earlier items than the third item. So all of this should be captured in this confusion matrix. And then you can use these matrices to kind of implement these different binding models. So in the temporal binding model, so binding via the ordinal position of the item that is presented, we would expect that if we have to use this ordinal position in ordinal queue condition to retrieve both items, we do so separately. So the probability of having a certain combination of color and shape response, so-called shape given the ordinal position, is just the product of the individual responses or response probabilities. Whereas in the shape condition, the probability of reporting a color and ordinal position given a shape should be the probability of reporting that color given that ordinal position times the probability of reporting that ordinal position given the shape key. And this probability here we would get from the results of the ordinal queue condition. We can basically from here see what is the probability to report with a certain color given the ordinal key, and fill that in here to give us the response probability in this kind of indirect pathway. As an alternative, we implement this object binding model. It is, to be honest, a bit ambiguous. So in general, I think the general problem that these object-based accounts are not very well formalized. So what we actually did is kind of just invert this model here, assuming that if participants are queued with a shape, they should make response errors independently, since they don't rely on the ordinal position to get the color. The color should be bound directly to the shape, so they should be able to retrieve that directly, and they should also be able to directly retrieve the ordinal position that is associated with this bound object. So yeah, this is relatively clear. In the other case, yeah, we just said they make it symmetrical to the temporal binding model, and we assume that if an ordinal position queue is given, you would kind of use that to retrieve the object that is also directly bound to the shape, and make the shape response, and then make the color response based on that retrieved shape response.
When I read the paper, I was a bit confused about calling that object binding. I mean, I can see in this logic that it's sort of probing the different ways how there could be independence.
Yeah, as I said, I agree that it's not entirely obvious that this is the object binding mechanism.
I'm asking because we've often thought that objects are localized, so that object binding is sort of binding through space, but that's not what is meant here.
No, that's so what is meant, and how I interpret the literature on that, or people who kind of argue for object-based representations, is more in the sense of an object file, where the features are kind of stored or very closely linked to each other, and so these are kind of sometimes called internal features or something, and other kind of external features like location of that object or the time when it's presented that aren't really. So if you have real-world objects, then of course their color and their shape are kind of permanently linked to each other, and where they are and when you see them are more kind of flexible.
I see.
Not so fixed.
I understand. Yeah, makes sense.
But for that, you really would have to introduce another kind of thing that is the object, and it's not really clear how to do that. So yeah, we basically just inverted that temporal binding model, the logic of that, which is a bit more obvious in the shape queue condition, that there getting the ordinal position one shouldn't affect your color response. Whereas here it's a bit hand-wavy, to be honest. That yeah, you should. I mean, you should see correlations. That if you select an object based on the ordinal queue, then you should report both that object's color and its shape. So you should have correlated errors there. If you get the shape wrong, there should be a high probability that you get the color wrong as well, and that's kind of reflected in this. So this behaves that way, although it doesn't necessarily implement an explicit object representation. Yeah, I mean,
so is the specific proposal in the object binding model that the shape is sort of the privileged feature dimension, or
in this particular implementation, it would be, but as I said, it's more intended to reflect the general properties that you should have correlated errors between the two features, which this one at least it does have this property, although yeah, I'm not entirely happy with it as the real implementation of object-based binding.
So would the sort of the symmetrical factorization of probability of color and shape given ordinal dimension, where you make it dependent not on the shape but also on the color, would be also feasible depending on
that would be feasible, but the problem is we can't compute that the probabilities here in this information for this task, because we don't have the information of how to get from color to shape, because color is here never used as a cue. So we would have to introduce another condition into the task to get the required information.
But you were not so interested in these different alternatives, I guess, right?
No, ultimately not.
I see.
Okay. Yeah, going to the results. So the interesting part where the models do make divergent predictions is when there's a swap error in the second response. Well, also the first response, but the second one is which we can investigate more directly. Since the first response is always color in both of these conditions, and so we can compare them. And the models make predictions about if the second response was a swap error, what will the first response look like? And the temporal binding model predicts that if the second response, the shape response, is a swap error, then they shouldn't affect the color response because they're independently bound to that ordinal position. So we would expect here that the most of the color responses are still on the target. Conversely, if in the shape key condition, if we have a swap error in the ordinal position report, then you would expect that that ordinal position that is reported there would also be used to retrieve the color, even though again the ordinal position is reported afterwards, but we may assume that it still has to be retrieved first to use it then to get to the color, and then it's also reported. And so here we would predict that if the wrong order position is reported, then we should see what is called a congruent swap. So the color at at that location is also reported, rather than the true target color. Our kind of object binding model makes kind of opposite predictions, that if you do make a swap error in the shape report, in the ordinal key condition, then that indicates that you have selected the wrong bound object, like an object file, and you should mostly see congruent swap errors in your color response. So you should respond to the color that belongs to the shape that you're reporting, rather than to the color of the correct color at the queued ordinal position. While making an ordinal position error, so swap error in the ordinal position, should not necessarily produce a swap error in the color response, because that should be bound, it should be somehow there in your object file or in your bound object presentation. The ordinal error shouldn't have an effect on your retrieving the color. And now the data that we actually saw, the blue bar in the middle, matches pretty closely to the prediction of the temporal binding model, both in that the target is mostly reported correctly when the shape error occurs, and that a congruent swap error occurs in most of the cases when an ordinal position error is made. That confirms and also is supported by formal model comparison using these kind of confusion matrices to predict the response, and fitting the models shows a much higher likelihood for the temporal binding model than the object binding model. We reproduced this with those of color and shape switched. So now the shape has to be always reported first, and then either the color with an ordinal position queue or the ordinal position with a color queue. And we still see the same pattern, although performance here is overall a bit weaker because shape is just harder to memorize apparently. If the ordinal position is queued, then we see largely independent errors. And if the color is queued, then we see a lot of congruent errors when a wrong ordinal position is reported, and also the shape at that ordinal position is mostly reported. So qualitative results from these experiments are consistent with each other and with the binding via ordinal position, with no evidence for bound object presentations in the sense of object files. Formal model comparison confirms that. It actually is tailored temporal binding model for all individual participants. And the results cannot be explained by just the fact that the memory for ordinal position is better than for the other features, because then you also see that, but that doesn't explain these particular kind of congruent swap errors that we observe in certain conditions. Then the next question is, after we've seen that, what does it mean for the spatial binding model if we now also have evidence for binding via time? So one possibility is that really binding via time is the dominant or even the real mechanism that we observe. And what happens when items are presented at different locations is that you just attend to them sequentially, one after the other, and just thereby basically impose a sequential order on them and use that to bind the features. That is kind of what the binding pool model proposes. That was devised by Sebastian Schneegans, also based on previous results they had on kind of the rapid visual stimulation experiments, rapid visual presentation, I think it's called. So where you present items very rapidly, one after another. And at some point, there's a cue in the sequence of visual stimuli, and you have to report the item that was presented there. Or there are two cues, and you have to report kind of two items. And based on swap errors there, they suggested that already kind of, so they call it a token that is assigned to the items in memory, which is kind of reflecting the ordinal position of an item in a sequence, and that is used as a kind of intermediate feature for binding, or as an intermediate dimension for binding the other features together. So yeah, that would be really using time, and it only looks like space because in the case of different locations, these different locations become associated with different times when the items are attended. The alternative is that spatial binding is really dominant, and that's the real mechanism. And in fact, it's kind of the opposite way, that when items are presented at different locations, you use that directly. Whereas when items are presented sequentially at the same location, you kind of internally remap them to different locations and also memorize then the order at which these locations, these remap locations, kind of come up. And you could just imagine then imagine that you kind of memorize the items as kind of in a line from left to right in the order in which they were presented. That you hold them in your memory like that. And so yeah, then space would be the dominant mechanism, and it only looks like you're binding via time because you are remapping different order positions to different locations. That has also been proposed by, I think, Alejandro is the author, but not really implemented as well. It kind of works out as a concrete model. Okay, so to kind of distinguish between these two possibilities, or kind of to tell apart the contributions of time and space, we did a third experiment in which we directly probed the binding of now color to ordinal position and location. It's again, to recall task where participants view a sequence of stimuli, not just color disks. The stimuli can appear at least 8 different locations shown here in the response screen around the center. There's 5 items in total. And yeah, there's also articulatory suppression, which was also used in the other experiment, by the way, so to make sure that participants weren't verbalizing the stimuli. Again, there are 2 cue conditions. So either now participants are cued with an ordinal position, and they have to report the color that appeared, for example, in the second in the sequence, and then the location where that appeared. Or they are cued with a location where one of the items appeared. So here to the right of the fixation point, where the stimulus was. And they have to report then first the color and then the ordinal position. So 1, 2, 3, 4, or 5. Again, there were some adjustments necessary in the task just to kind of get the right difficulty level. Memory for sequences of locations is really pretty good. Whereas memory for sequences of colors or kind of color locations is a bit more difficult for people to remember. So we used a fixed set of highly discriminable colors to make that a bit easier. We also had the special kind of rule that the last stimulus was always white, and participants knew that was the case, so they didn't explicitly have to memorize that final color, which made it a bit easier to memorize the other color. And that last item wasn't that interesting anyways, because there were very few swap errors there for us to analyze, so we didn't really lose much by that. And yeah, we had a set size of 5, so again, a bit larger than the previous task, closer to that spatial task in the beginning, and that gave us a decent performance, but also a relatively high number of swap errors occurring here in this task. Again, the overall results here in the ordinal key condition, reporting color in blue and location in purple. Again, we had categorical response options with the 5 options for color that were actually in the display and the foil color, and yeah, all the 8 possible locations, so 5 or 1 target location for basically swap locations where items did appear, but also target item, and yeah, the other 3 were in foil locations. What can you see? Performance for the color report that had to be done as first response in both of the tasks was relatively similar between the 2, although you see a bit more kind of ordinal effects in the ordinal Q condition, as you might expect, so that they see a bit of a primacy effect in addition to a recency effect. Of course, keep in mind that this final report here of the color of the last item is trivial because it was always white. But yeah, overall performance between the color reports was similar, and report performance was good for both location and for ordinal position. We again see significantly more swap errors than you would expect if the kind of the incorrect responses were just purely random. And once again, then ultimately what we're really interested in is the kind of correlations between the swap errors. So same analysis as before. We look at the trials where participants make a swap error in their second response and see what the first response, what the report looks like there. So in the ordinal Q condition, that second response would be a location. If they select a wrong location, what would we expect the color response to look like? And if the ordinal position is really the binding dimension, so temporal binding model, we would expect then that the color response should be mostly correct, even though the location is selected incorrectly. Whereas if they queued with a location and they make an error in the ordinal position report, then we would expect that they have used that ordinal position that they have reported also in retrieving the color, and so we should see mostly congruent swap errors. Again, so the height of the bars is computed from these confusion matrices that we observed in the different conditions. Conversely, the spatial binding model is just the opposite. If the color and ordinal position are bound via their location, then you should see here congruent swap errors when queued with location. Congruent swap errors when queued with ordinal position, because then you have to go from the ordinal position to the location and from there to the color. So making an error in the first step should lead to a correspondingly wrong response in the second step. Whereas in the spatial Q condition, you can directly go from location to color and ordinal position. So you should make uncorrelated errors. And the results in this case were really quite exactly intermediate between these two predictions. So
I was actually going to ask why there has to be dominance of one over the other.
Yes, I mean, there was of course a bit of a setup
right.
for the there might be both, and that's what it looks like.
Right.
So yeah, on average, these the real results are intermediate between the predictions of the two models. There is quite a bit of variation between participants. So some do show a preference for ordinal or spatial binding, or at least show kind of behavior that would be consistent with those. But none of them really very strongly. And so yeah, in the formal model comparison, I think was slightly more. I know which one. Maybe slightly more participants were best fit with the spatial binding model, but the average was more in favor of the temporal binding model, or maybe it was vice versa. But anyways, there was no clear outcome that either of those is preferred. What do we have here? So this is kind of ambiguous. There's one more thing we looked at, and that is the gaze direction or the gaze biases in the ordinal Q condition. So here we have this case that in this task, in the ordinal Q condition, people see this ordinal position, so the number in the center, and they always have to first make the color response. And we recorded the gaze during all these tasks, mainly just to make sure that people were looking at the screen and paying attention to the task. But afterwards, we realized that we could use that to see a bit of what may have been going on in their head. And so we analyzed immediately after the cue appeared, where were participants looking at? And of course, they to some extent should be looking at the colors, But what we found is that participants did have a gaze bias, that they looked more often towards the location where the item appeared immediately after the cue was shown, before making the color response. So this is always the direction of the cursor card after the onset of the ordinal cue, and that is found in the majority of participants, I think in all of except one. I mean, it was only 10 participants, I think, but yeah, it was relatively consistent that most of them showed a bias towards making the cursor card towards the spatial location where the cute item was.
So that's a location that at that moment in time is not perceptually marked. So it's not
exactly. So there's nothing there. The locations are all marked equally,
right.
And they do not at that time. So they first have to make the color response, but they still, at least some of the time or more often than you would expect by chance, look at the location where the item was before they actually make the color response and look at the color stimuli. So there does seem to be some kind of automatic recall of the location induced by this ordinal cue.
Outstanding.
So yeah, what does it mean? So yeah, just to summarize again, as I said, results intermediately the two-model prediction, also in full-world comparison. With yeah, there's here a majority of participants better fit by temporal binding, but the mean likelihood was in favor of the spatial binding. We also didn't, so that was another possibility that we considered, that we might just see spatial binding or results consisting with the spatial binding if we use the spatial cue. So basically, yeah, okay, that that kind of see that you would always see independent swap errors. That if there's a spatial cue, you use that to retrieve both the color and the ordinal position independently. And if there's an ordinal cue, you use that to retrieve both items independent or both features independently. So that we should never see congruent swap errors. But we do see some proportion of congruent swap errors, more than you would expect by chance. Keep in mind here that in interpreting these results that there's always more options to make incongruent swap errors, because just there are 5 items and all the other colors would be incongruent swap errors. And so just by chance, this bar here, or this bar for the incongruent swap errors should be then 3 times as high as the bar for congruent swap errors. And so that's also not what we see. It's not that people just can use either mechanism equally. So what might be going on is that people do retrieve the ordinal position or the location first from the cue, and then can use both of these so both of them to some extent to retrieve the color information. So that color is bound both to ordinal position and to location. Location and ordinal position are of course also bound to each other, and I mean that is what we have seen and what we already know from before, that performance for or memory for location time bindings is pretty good and reliable. So kind of the hypothesis is, I'm not sure, I think I really have written it down here, a possible explanation is that the retrieval of the location from the ordinal position or vice versa is pretty fast and reliable. And then both of these can be used to try and retrieve the color, so that there are conjunctional representations for location and color, and for time and color, and of course also for location and time. And if you make an error in your kind of, for example, retrieving the ordinal position from the spatial location, then you have 2 kind of competing cues for retrieving the color, and sometimes you pick the right one, and sometimes you pick the wrong one, and so you sometimes get the right color, and sometimes you get these congruent swap errors. That would be kind of the idea. And yeah, one thing that goes a bit into the direction is that there has been this discussion going on about dynamic memory representations, kind of attacking or questioning this idea that you have really sustained activity, that some neurons that are representing memory features are just active for an extended period of time during the memory or over the whole memory period. In several fMRI studies and also electrophysiological experiments in animals, it's actually quite often that you see relatively little generalization from one point in time to another during the memory period. So that there has been the kind of argument that really it's just a sequence of activations that's happening rather than a sustained over peak. We would consider a sustained peak in one field. So there has been, this argument is really completely dynamical. But even more recently, there have been several studies that have indicated that there still are stable subspaces in these representations, so that you can still stably decode the features, even though there's also dynamics happening there. So the representation does change, but only some aspects of it. And there are some activation patterns that remain stable. And so that could be consistent with that if kind of the feature time binding is implemented as a kind of dynamic field, or well, not a dynamic field, but as a field in which a peak is drifting over time. For instance, I think in Portugal, so Wolfram and Estella, you did have some models like that, where peaks just kind of continuously drift to reflect the kind of the time since the stimulus appeared. So that could account for the dynamic part of the representation. You could mention that, for example, the time axis is kind of arithmetically, so you get a relatively fine resolution for the most recent events, and then more and more compressed representations for things that are more distant in time. And ultimately, they will kind of squish each other out or be pushed away or destroyed by more recent stimuli.
You're referring to here, is that neural data or is it psychophysical data there?
So on this slide here, this is neural data. So this is either fMRI recordings or electrophysical data from monkeys. And I did have some more references from that.
So we've, as you know, have used this idea of binding through what we call an index through an ordinal dimension in sort of higher cognition, when you refer to really concepts and objects that have names and so on and relations. And so in that picture, both are relevant because ultimately you will build a index map. That is, you will have an explicit representation of the order and location, which would be important for instance, like a little scene representation where you can look back to an item. So that would serve different purposes, would be important for longer lasting things. And we know that, even a little scene will be in long-term memory. Actually, it's not just working memory. You will very quickly build it's just sort of like a mini version of a navigation, of a spatial map. And in that map, the ordinal dimension might be an important dimension. So I think neural processes, there could be also the process that support such things, but there could also be, of course, additional structure, maybe even involving map formation that...
Yeah, of course. What I sketched there was more the perceptual level, so just memory for stimuli. And
I put that paper here in the... Yeah, sorry.
So if you go to higher levels, that might really be replaced by something more categorical, it's also more categorical in time, so you really have.
For instance, Minsiok's work on analogy, which we reported a couple of weeks ago, uses that idea, that is that you would have different maps and for different objects or different scenes, and you could even link the objects in different scene through that index. So that,
well, I'm still a bit skeptical, or try to be careful with, and we talked about that as well before, that having maps over kind of like object labels is something that I'm still entirely comfortable with, or that I feel is challenging how that will really be implemented.
Exactly, and actually we introduced this index idea in part in response to this difficulty. That is, rather than be able to have, a spatial tuning curve for every concept, you just need that every concept has some capacity to store a ordinal index, which would play a role in establishing, for instance, across different phrases, like nested phrases. You would be able to relate that it's the same thing that I mentioned in the previous phrase that I'm referring back to. That's where that idea comes from. But then you don't actually need to have a spatial map into which you put the object. And I think that is one of the difficulties of the semantic maps people are talking about, right? That I find that quite problematic. And potentially this could provide a mechanism. It's highly speculative, I would say much. I mean, I'm so elated that your work gives a little hint of some evidence that would support ideas like that. We just invented those things without really having any evidence, but it would solve these theoretical problems in part, I think.
I mean,
actually
I mean, we don't use explicitly something like an index, but we have this joint representation of feature and time. The temporal information is encoded in the bump height. And then we use this kind of temporal binding. We have gradients, first, second, third, for different features. And then the bumps, which evolve synchronously and reach the readout threshold at the same time, they are binding the features. So we use explicitly this kind of temporal binding here. We have different parallel sequences, independent sequences, of stored and learned for different features, and they evolve synchronously in time and reach the threshold at the same time, and that's why they are binded.
That's so it's really, the mechanism really for that, right?
Yeah, that would be the space, temporal coding, where you have a dynamic which evolves, but also working memory where you have really bumps with different amplitudes encoding the temporal order, for instance. So we actually use this in episodic memory tasks and so on. We have this kind of temporal binding there.
Was this your last slide, or did we?
I think yes. I think it's just conclusions.
Just I jumped in because this was right on topic.
Yeah, maybe just briefly. So Harrison, who had done this experiment on the temporal crowding, and then also involved in this temporal binding paper. Justin McMaster did much of the experiments from the first temporal binding study, and Paul Bayes was my supervisor in Cambridge.
Well, outstanding work. We're really extremely excited about this. As I mentioned, this I would say overall, I would say this is consistent with what we have often postulated, without necessarily having all the empirical grounding for that. That space does play this special role, and I think that's very, very consistent. And then on the other hand, I think since Julia's work on what we call this ordinal machine, so that we know that we could extract ordinal information and store it, that that could play a similar role is solves theoretical problems, and it is actually extremely exciting to see some evidence for that. And rather, I could never have thought of that. It's very impressive. Wonderful. So are there any other questions or discussions points you want to raise, please?
I mean, Sebastian, do you want, I mean, you in your paper, you are referring to this probabilistic framework. I mean, you are thinking also working more, elaborating this in the DNF framework, or is it, I mean, do you want to go in this direction to include this in temporal binding aspects as well?
Well, as you may or may not know, I'm actually no longer working in academia. I'm no longer working with direct field, so I'm working now as a kind of data scientist and algorithm developer for diagnostic medical devices. So I don't have much time to develop DFT models. It's still something that I'm interested in, and sometimes I do. So I still do read some papers and think about them, but yeah, it's not something that's going to happen very soon.
And in the person you mentioned in Paul's lab, or he wasn't there, but he was collaborating. Does that person? I don't remember the name. Is that person?
Ivan Tomic.
Yeah.
He is now so he's still in academia as a lecturer in Croatia. So he's originally from Croatia and went back to there after he left Paul's lab. And he's still working with Paul, so he's not really working on neural dynamics models. But yeah, there was this one paper that kind of somewhat bridges the type of model that Paul Base is using, so these really spiking neural models, but so not implement connectivity, but more kind of analytical spiking models where you describe how spiking activity could be optimally decoded. And so bridging that or linking that to the neural dynamics and the DFT framework. I actually haven't spoken to him yet about maybe presenting something here. Yeah.
Maybe we stop screen sharing and then we'll see each other a little bit
better,
depending on what kind of screen you have, actually. Yeah. Good.
One thing I just wanted to say earlier when we were talking about these semantic maps. So there actually was one experiment idea that I've had for a while and that I never had the right. So I wanted to do in Cambridge, but never had the right stimulus set for that. That's also coming a bit in this direction. So testing for swap errors to see. So use kind of naturalistic stimuli. Like of little images of objects in the display where you're in a cubicle location and have to report the item there to test whether kind of semantic similarity affects swap errors in a similar way to kind of feature similarity. So we have in our models, I haven't talked about that much now explicitly here, but one key part of the models is that swap errors occur mainly between items that are similar in the cube feature. So if you are cubed with this, in one example, that is orange color, and so it's relatively likely that you will swap in a response based on an object that was red or maybe yellowish, and less likely that you're going to swap in something that's blue or green. So feature similarity should affect probability of swap errors between items. And I thought that you could use that also to test whether semantic similarity this has an effect. That you cue, for example, with the kind of a label of an item, so say the mug or the hat or whatever is the cue, and you have to report the location of the item. Would you there see kind of swaps based on semantic similarity between like I know kitchen items or different pieces of clothing, or only between really perceptual similarity? So if the items are kind of rounded in the image or kind of elongated or oriented in a certain way. I thought that it might be interesting to get at this idea of semantic maps. That if there really are presentations like that at higher levels, or whether it's all just kind of dynamically bound to the lower where you know that I know a mark has a certain shape. And
interesting that you ran into that idea, because we're thinking about something like that from a very different motivation, I mean, theoretical issues. Because if you think of the machinery, I put this paper of Daniel's here in the chat, by the way, where this index stuff is explained. And if you think about that, connected to what we earlier said, if you have all the concepts, and these would be just a few neurons, let's say populations of neurons for different concepts, let's say, and you'd have to give them some shared dimension which would keep track of the ordinal position they're in currently. And that's how you could build maps of that and all that. And you can see if you have hundreds of thousands of such concepts, then it becomes nearly a bit unplausible that they would all have shared projections synaptically.
Yeah.
And so it would be possible that you have subpopulations that are not as fully bindable because they're not sharing these same kind of ideas. And I think that's a little bit what you're hinting at, or could be related, I think, what you're hinting at.
Yeah.
So I have you on both screens here. So that, that if you are within one domain, maybe binding through ordinal position would be more effective than if you're going across domains, like these very strange sentences linguists sometimes use where they don't make any sense. Maybe one could predict that then it's harder to bind. And one could maybe think about, for instance, in nested phrases. Do you do that right? I don't know if it will show up at this really psychophysical level. That's maybe the question. Or is this a bit more abstract? It doesn't really show up in an experiment like that.
Yeah, I guess I was coming really more from the psychophysical level, so from the low level, and thinking about whether that the speech similarity effects extend to the higher level. And actually, my expectation would be that, from rather not, that you really just have the kind of binding features to locations, but not objects. So not kind of the mark or the head or the whatever thing is at a location, but just that the features are there, and you know that what features belong to a certain object from your long-term memory. And so it's only this kind of low-level.
Remember, Larissa and Linda Smith is associating a label with a location for linking to an object. That would be an example. Of course, you could now think it's an acoustic feature, like maybe the.
I guess there was only a few objects that you kind of learn repeatedly in a short time frame.
Jason, we don't hear you. Maybe your microphone, even though you're not muted. No, it must be something else. Now you're muted. Is your microphone not working? We still don't hear you. Maybe I look under Zoom, under the audio button of Zoom, if you have selected the wrong microphone. That sometimes happens. Still don't hear you, I don't think. No, I don't hear you. Bad.
Maybe you can write a question in the chat as well.
Technology. Always funny. Microphones and cameras are always the problem. More and more programs connect to your hardware, and then there's conflict sometimes. This one typing. Okay. Now we can see how fast you can type.
And no, in these experiments, we always had distinct colors and shapes for the items. But I guess that might offer interesting opportunities. I mean, I have been thinking about that in the context of the spatial binding, when you have multiple items with the same color. It actually was that was something. So I was thinking about that in the context of the DFT models, where that is actually it's a bit difficult to tune these models to work reliably if you can have multiple instances of the same feature. Because when you run into the problem that, well, that feature is necessarily stronger, like in a selection decision between colors, then just having 3 instances of the color may lead that color to win, even if you have kind of are attending to a different one. And I mean, there are, I guess, mechanisms in the visual system that you do kind of tune down the activity for features that are represented multiple times. So that, I mean, you have these effects of pop out of one color, everything else is another color. But yeah, to actually tune a DFT model to deal reliably with all of that has been difficult.
In this, generally in DFT, you have these magic effects. If you're very close, there's a difference how close you are, and that could be in any of those dimensions. And sometimes, you know, we've really seen consequences of that. That's part of the tuning problem, that these magic effects then can destroy the function under some conditions. And sometimes that might be real, but it's not always. Yeah, see you in Rotterdam. Looking forward very much to that. Yeah, we'll probably need to close. Everyone needs to leave. This was extremely exciting. I'm very, very happy, Sebastian, to have you here. Maybe if you have a moment, could I have a word with you, perhaps, Sebastian?
Yeah.
After this, yeah. Yeah. So I'm looking forward to seeing many of you in Rotterdam. Maybe not everyone, and perhaps many of you would be able to join us for that DFT Fest after the DFT school. So 17th of August, I'll send an email around about that. And we'll make a lengthy free discussion kind of session in the afternoon then, in our European afternoon, so in the morning for US participants. We're very happy to have many of you join us then.